So a perceptron uh, okay, a perceptron is basically a simple unit which has two parts. The first part of a perceptron simply compute a weighted sum of inputs. So suppose that you have a d-dimensional vector, and this d-dimensional vector is the input. Basically, you have d features or d variables for an object. And this is the input of your perceptron. What's happening in this part of perceptron is to compute a weighted sum of these d measurements. So basically here, it's going to be some beta 1 times x1 plus beta 2 x2 beta d xd. So here I basically have this summation, beta I x I for I equal 1 to d. Sometimes I add a scalar to this, beta null. So in vector form, if beta is a d-dimensional vector, what's happening here is beta transpose times x, when x is a vector and beta is a vector. Okay? So the first part of perceptron, this part of perceptron, would be simply a weighted sum of inputs plus a beta null. The second part of the perceptron is a nonlinear function, which is usually called activation function. When we apply a nonlinear function to this weighted sum, traditionally this activation function is a step function. So if beta transpose x plus beta null is negative, when you apply a step function to it, the output would be negative 1. And if it's positive, the output would be positive, plus 1. Okay? So the output of the perceptron is either negative 1 or plus 1. And traditionally, it has been used to classify two classes. Suppose that the label of one class is negative 1, the label of the other class is positive 1. And then you want to set these weights, beta 1 to beta d, and beta null. These are parameters of your model. You want to set them in a way that the output basically predicts the label of the class. So if you choose one object from class 1, the output is 1. If you choose an object from class negative 1, the output is negative 1. So we want to predict the label correctly. Okay? So to find beta and beta null, as I told you, when it was invented in 1958, they didn't know how to train the weight, how to train the perceptron, and they used to randomly change the weights until it works for some problem. Later on, we learned how to train, okay? And by training, I mean how to find beta and beta null. To find beta and beta null, we need a cost function. We need an objective function. In general, in any machine learning algorithm, there are 3 steps. The first step is that you want to model your data using a function f. And this function f, you're assuming that it comes from a hypothesis class. You have to make some sort of assumption that which hypothesis class can model this data. So I assume, for example, that a linear function can model my problem. So my hypothesis class is class of all possible linear functions. Okay, I may assume that a quadratic function, a polynomial function in general, is going to model my problem. So first I assume that there is a hypothesis class and my function comes from this hypothesis class. Okay, and we always have this step. No assumption, no learning. This is famous no free lunch theorem in machine learning. Okay, no free lunch theorem basically says if you don't make any assumption, you can't learn anything. You have to make some assumption. Okay, so we assume something about data. We assume that a function comes from hypothesis class. And the second step is that, okay, in this hypothesis class, there are many members. Which one I'm gonna choose, you know? The set of linear functions. Which linear function is going to fit my data the best? So how I'm going to evaluate, if you choose one member of this hypothesis class, how I'm going to evaluate this member. Is it good? Is it bad? So I need to basically score them. And this scoring is what's called a cost function or objective function. And then we need to find, you know, I have a scoring function. So basically, I can, among all elements of this hypothesis class, I can score them. I have to choose one among all. And there's a search strategy to choose one. And this search strategy is optimization. You know, you form it as a convex optimization problem. You can make it convex. It's non-convex. You use gradient descent, stochastic gradient descent, conjugate gradient, Newton method. You know, you have a search strategy to find that one. So in this case, our hypothesis class is class of linear functions. So we are assuming that there are two classes to be classified. So positive labels of one of them, and negative is label of the other one. And I assume that a linear function is going to classify them. So this is my hypothesis class, function of linears. And there are many of them. Then I need a scoring function to score them. Which one is better among this linear function? Which one is better? And then I need a search strategy to find one. So the fact that it's linear, I told you, you know, it was not clear in 1958. It took many years for researchers to realize that it's just a linear discriminant function. But we know it now, that perceptron is just a linear function. We need a cost function, and you can have many different cost functions. You can score them in many different ways. And based on the way that you're scoring them, you get many different algorithms, you know. So again, traditionally, the way to score them is to find the distance of all misclassified points. So basically, among all possible lines that can make distinction between these two classes, I'm looking for the one which misclassifying points less. Not only misclassifying points less, but the distance of the discrimination function or the hyperplane is smaller compared to other possible cases. You know, the score of this one compared to the score of, say, for example, this one. You know, in this case, no point has been misclassified. So the summation of points that have been misclassified in this case is 0. In this case, there are points that have been misclassified. This point is misclassified, and this point is misclassified. So I'm assuming that everything on one side of the hyperplane is negative, on the other side is positive. But it turned out that these 2 points are on the left side, supposed to be negative, but really they are positive. So they have been misclassified. So the distance of these points to the hyperplane, the summation of these two distances, is my cost. So I have to minimize this. I don't like this. I'm looking for the hyperplane which has minimum distance of misclassified point to my hyperplane. So this is we decide to choose this objective function. You can decide to have many other objective functions here. It could be just the number of points that have been misclassified. It could be, cross entropy, for example, which we haven't learned about yet, or likelihood, something else, But we choose to have this cost function. Okay. Now what I have to do is to write this cost function in a mathematical way. Okay. So I have to basically distance of all misclassified point, write it in a mathematical way. Okay, how to... we know that the perceptron is just a linear discriminant function, and any linear function can be expressed in this form. Okay, let me tell you a little bit about geometry of this hyperplane. Learn a little bit about the property of this. If I choose 2 points, x1 and x2, on this hyperplane, then both of them are on the hyperplane, so they satisfy this equation, beta transpose x plus beta null equal to 0. This is the set of points that satisfy this equation. So the first thing that I can say about this is that beta transpose x1 plus beta null is equal to beta transpose x2 plus beta null. And it's equal to 0. Because both of them are on the hyperplane. So it means that beta transpose x1 minus beta transpose x2 is equal to 0. And it means that beta transpose x1 minus x2 is equal to 0. So x1 minus x2 is a vector. Okay? So this is a vector. And beta also is a vector. And now I tell you that the dot product of 2 vectors is equal to 0. So what do you conclude out of this? The dot product of 2 vectors. It means that these 2 vectors are orthogonal, right? It means that beta is orthogonal to x1 minus x2. So it means that if you have the equation of hyperplane, that beta is orthogonal to the hyperplane. That's first property. Second, for any point here, for any point x null, we know that beta transpose x null plus beta null is equal to 0. It means that for any point, beta null is equal to negative beta transpose x null. Right? Okay, now suppose that I give you a point here, x, and I want to compute the distance between this point and the hyperplane. Don't forget that our cost function is the distance of all misclassified points. So first, I need a way to find the distance of points to the hyperplane. So I have a point x, and I would like to know the distance of this point to the hyperplane. I would like to compute this distance. Any suggestion based on the properties that we learned? Yes?
Euclidean norm, like the norm between 2 vectors.
Which 2 vectors?
x2 and x, which is the one on top of it.
This is x.
Yeah. And compute the norm between that and x2 minus x1.
Okay, and how does this help?
Well, we know the
So that would be that would be basically Euclidean norm between x and this vector.
Yes.
But I need this.
Okay.
Yes.
You can find the projection of the point on the hyperplane and moving along the direction beta.
Okay.
And then once we have the projection, we can compute the distance between those 2 points.
Right. Yes, exactly. You know, I need to project this on this direction, on the direction of beta. So this point, you know, let me erase these things. I call this point x naught. Okay. It's trivial to find this distance, x and x naught. You know, I can just subtract x minus x naught. But to have the distance, I have to project it in this direction. And that would be my distance. Okay? So basically, to find this distance, I can simply compute x minus x null and then project it in the direction of beta. Project this in the direction of beta means compute beta transpose times x minus x null. Okay? Does it make sense? Okay. So beta transpose x minus beta transpose x null. Minus beta transpose x null is beta null. So beta transpose x, negative beta transpose x null is beta null plus beta null. So beta transpose x plus beta null is this distance. That's what we are looking for. Give me an x, and the question is that what's the distance of this given point to the hyperplane? So the only thing that you need to do is to put this in the equation of the hyperplane. Okay? But we are not quite done, actually. You know, if the point is on the hyperplane, beta transpose x plus beta null is equal to 0. If point is not on the hyperplane, if I'm on one side of the hyperplane, then this is going to be positive. I'm on the other side, this is going to be negative. If I'm the same distance from the hyperplane here and compute this projection, this is going to be negative, and this side is going to be positive. When I'm talking about distance, distance is always positive, right? I don't care that the point that has been misclassified is misclassified on this side of the hyperplane and on the other side of the hyperplane. I don't want any point to be misclassified. Okay? So I'm looking at the distance, not sign distance. So the distance, you know, this could be positive, this could be negative based on the sign. I want it to be positive all the time. What should I do?
Class label.
Sorry?
Class label.
Class label what?
Multiply this one to class label.
I can multiply this to class label. Okay? So if I'm on this side, everything's supposed to be positive, so multiply to positive number is positive. I'm on this side, everything is negative, multiply to class label, become positive, right? I can also take absolute value. Why don't we take absolute value simply?
It's not differentiable?
It's not differentiable, you know. I mean, for cost function, it's important to be differentiable. Non-differentiable cost function doesn't help us in search. So always we need a cost function which is differentiable. So I can take absolute value simply, but I don't do that because then it's not differentiable. But I can multiply this by class label. So basically, my d distance would be class label for point I, would be class label times beta transpose xi plus beta null. So that's my distance of point xi to the hyperplane. Yes.
Transpose has to be unit vector.
Sorry?
Beta transpose has to be unit vector.
Beta transpose needs to be unique.
Unit vector.
Yeah, that's a good point, actually. You know, beta needs to be unit vector, you know. I mean, if you want this calculation to be precise, when we are talking about distance here, you have to make sure that beta is normalized, means that this beta should be divided by the norm of beta. You know, everything needs to be normalized. You have to divide by. But I simply assume that these betas are normalized. You know, you can, whatever the beta is, beta transpose, divide by the norm of beta, I call it beta. You know, I assume that these betas are normalized. But you're right, it's supposed to be normalized. Okay, this is the distance of a point to the hyperplane. So remember what was our cost function? Summation of all distances of misclassified points. Points that have been misclassified. Points that are misclassified are on the wrong side. Right? So the sign needs to be flipped. You know, the positive label is on the negative sign. The negative label is on the positive sign. So for misclassified point, actually the distance is negative yi beta transpose x. And then my cost function, which is a function of beta and beta null, is simply the summation of this minus yi beta transpose xi plus beta null. Is that clear? Okay. So we have a hypothesis class of linear functions. We have a scoring. So I'm going to score them based on the distance, the summation of distances of misclassified points. Now I have to minimize this. I have to minimize this cost function because I'm looking for the line. I'm looking for discrimination function which has the minimum distance to misclassified points. So if I classify everything correctly, this is 0, for example. You know, and if I classify them in a wrong way, then I have to pay some cost. Yes.
So the solution is over all points or just
Over all points that have been misclassified on set M, and M is a set of points that have been misclassified. Not all points, only misclassified. Okay. So I need to minimize it. Basically, I need to find beta and beta null in a way that this is minimum. How can I do that?
Use derivative.
Sorry?
Use derivative.
Take derivative, right? So I have to take derivative of this function with respect to beta. And I need to take derivative of this function with respect to beta null. What is the derivative with respect to beta? Sorry? Negative yi xi. And what's the derivative with respect to beta null? Just negative yi. Right? So I have derivative. So now I have the derivative, so what's beta now? What's beta now? You know, there are many different search strategy. There's many ways to optimize the cost function. Sometimes you have closed form, sometimes you have to use numerical method. A method that is common in neural network is gradient descent. And gradient descent basically means that you have a cost function and you need to take to this point. Gradient descent means that I'm at this point. I take the gradient. Gradient is tangent to the surface, right? So that's gradient. That's tangent. Basically, it tells me the direction toward the minimum. And then I will take one step toward the minimum. Then compute the gradient again. And gradient will tell me the direction again. And then toward the direction, I will take another step. It's a very simple algorithm. It's called gradient descent, right? So at each point, I will take one step. And then I take the gradient again. And I take the gradient again and again until I get here. In fact, in gradient descent algorithm, there is no guarantee that I get here. You know, it's possible that this is just a local mean. So I get here, and then I take the gradient, and the gradient tells me that's a good point, stay here. You don't need to go anywhere. But that's wrong. I need to go here. That was a problem for backpropagation that we are going to learn, and in gradient descent in general. That was a problem for neural network. That neural network doesn't have a convex cost function, it's non-convex, and it's quite possible that you get stuck in local mean. That was one of the main complaints about neural network. But you don't hear this complaint anymore. The reason is not that gradient doesn't get stuck in local mean. The reason is that when you are in high dimensional space, there are many local means that are as good as each other. Means really it doesn't matter if you get stuck in local mean in high dimensional space. And now we are working with very high dimensional space, so we don't see the effect of local mean as we used to see in the past 20 years ago. 20 years ago, your data was two-dimensional, three-dimensional, and when you optimize, there was a great chance that you get stuck in local mean, and there was a great chance that this local mean is really bad local mean. Okay, but there are mathematical reasons behind that. But intuitively, you can appreciate the fact that when you have a local mean like this in two-dimensional space, it's quite possible that you get stuck here. But just imagine that this surface is three-dimensional. If it's three-dimensional, there is some chance that you can escape from the third dimension. Even when you're stuck in this two dimension, there's a chance that you get stuck. You can escape from the third dimension. Okay, and with like modern data that the dimension is hundreds, sometimes millions, right? There are quite a high chance that there is some way to, escape from the local mean and eventually get to a point that, so that's the reason that you don't hear more or you don't hear often about the problem that used to be a very serious problem for neural network 20 years ago. But you don't hear this anymore because we're working with high dimensional data. Not because we have a better search strategy. Yes.
Doesn't your training stop the moment you converge at a local minimum?
Sorry?
Doesn't your training stop the moment you converge at a local minimum? Even if you have many chances to escape, if you converge at a local minimum? Yeah,
you converge to local minimum, yes. I mean, there is no guarantee that you converge to global mean. You converge to local mean. But the point is that in high dimensional space, there are many good local means. Many. So you converge to local mean, but it's a good one. It's not a disaster, usually. Could be a disaster, but usually it's not. Okay? So gradient descent actually, as I said, it's just, a procedure that when you want to find beta, your new beta is the old beta minus a small step toward the gradient. So you take gradient, it's basically direction towards the minimum, and then you take one small step. This is called learning rate. And learning rate tell you how large or how small your step should be. Large lambda means you take a large step, and a small lambda means that your step is small. Should we go for large or small?
Somewhere in between.
Why?
Because if it's too big, then you might step over the local minimum.
Okay.
You can just pass the global minimum.
If it's too large, it's possible that I'm here, and I want to take one step, but this type of one step means that I will jump here. And then I take a big step again, and then I will jump here. I never see this point. And if it's too small, the learning will be quite slow, because I take very small steps. So in fact, in practice, the learning rate would be adaptive. So we start with the large, and then we make it small when we are closer to the point. Okay. So these are the properties that I told you, and as you mentioned, this vector needs to be normalized, but I just assumed that it's already normalized. And then you have this cost function, and then gradient descent basically would be a procedure of this form, and for this case, actually, since the gradient the derivative with respect to beta is this quantity, and derivative with respect to beta null is this quantity, your algorithm have this form. Okay? You can update your beta and beta all until it converges. That's traditional way of doing perceptron. Okay? So you can change this cost function to another cost function, and then it's going to be identical to logistic regression, for example. Okay, there are some properties about perceptron. One is that if data is linearly separable, theoretically it's guaranteed that the algorithm will converge to a separating hyperplane. If data is linearly separable, sometimes data is not linearly separable. There is no line. If there is a line, then it will converge. But the number of times, the number of iterations, the number of times that you need to go through this until it converges depends on the gap between two sets. So I said they're linearly separable. Linearly separable means that for beta transpose x plus beta null, there's always a constant, okay, such that this is greater than equal that constant. So there's always some distance to the hyperplane. This means that it's linearly separable, and this is the gap. If this is a small, it's hard to converge. So two data sets are close to each other. There's a small gap, hard to converge. They're well separated, easy to converge. Okay, so the solution is not unique because it's not convex. It's going to get to a minima. So it depends on the initial value, you're going to get a stuck somewhere. Okay. And so a perceptron can only discriminate between two classes. That was something that It's trivial now, but it was not trivial, as I told you. You know, for many years, people thought that they solved AI with perceptron, and then they realized that no, it's just a linear discriminant function, and people were surprised that they can solve XOR problem using perceptron. So they were surprised that, okay, it's linear. They can do that. Okay, I told you about the small gaps, so these are not important. You can see them later, and this is the definition of gap between and definition of linearly separable, and the convergence rate depends on this constant. So I skipped them. So let's, if there's no question about perceptron, let's get to neural network now, which is basically, collection of these perceptrons. Any question? Okay. So neural network and feed-forward neural network, as I told you, is layers of perceptron. Okay? So instead of one perceptron, I have one layer of perceptron and another layer of perceptron. And so for one perceptron, I had this input and one output, which could be 0 or 1. Now assume that you have inputs here, x1 to xd, and then instead of one perceptron, you have many of them. And, this goes to everywhere. And then they have some output, but this output goes to another layer of perceptrons. So this goes here, this goes here, this goes here, and so on. So basically, each perceptron is linear sum of the input and then a nonlinear function. And you apply this many times. So it's a composition function, right? F of something, which each layer is one of those f's, one of those sub-functions of a very complicated function.